Hey guys, this is video 13.1. We are now starting our new unit on kinetics and equilibrium. So we're going to start with talking about the whole reaction process. Now we've been talking about reactions for months. You guys have written reactions, you've done solubility with reactions, you've written net ionic equations, all that type of stuff. But now we're going to start getting into the mechanisms of the reactions, kind of what's actually going on at the molecular level. And that is known as kinetics, okay? So that is the study of the rate or speed at which reactions occur, okay? So one thing, just as a side note, guys, when I ever see RxN or RxNS, it just means reaction, okay? It's kind of the shorthand way, or my shorthand way, whatever you want to say, for reactions. All right, so if there's an S on there, it just means reactions. So if you think about it, maybe you've thought about it already. We've talked about it. It's been a while since we've talked about, bonds breaking and bonds forming, but that's exactly what a reaction is. It's the breaking and reforming of bonds. And what that does is it makes an entirely new compound as products, okay? So your reactants are on the left side. That's what you start with. You break those bonds. The molecules, the atoms, they start rearranging, and now they reform new bonds, making new compounds, okay? So that shouldn't be anything, groundbreaking to us, but again, we're going to kind of talk through the process with it and show some things like heat of reaction and kind of the energy that's associated with it. So what that is and what shows all of those bonds breaking and forming is called the reaction mechanism. So that is the step-by-step process that's needed to make a product. So it's how you get from A to B, kind of like a recipe, all right? So different reactions occur at different rates. That shouldn't be anything that's super crazy, out of this world, brand new to us, because things have different sizes, they have different masses, things just take differently. It takes more energy to break some bonds versus other bonds. So it shouldn't be, again, groundbreaking that reactions occur at different rates. It's important for chemical engineers to know the rates of reactions so that they can then use that in the production of certain chemicals. So anything like, let's say toothpaste, for example, they need to know how to make those, how they come together. So if they want to produce, X amount, all right, they can do the calculations, but they also need to know how much energy and how long that process is going to take in terms of like price and selling and, product production steps. So what determines the rate of reaction? Well, there's two things that actually determine the rate of reaction. The first is the number of steps. Now, this is very, very important for us to kind of make note of. So the more steps can, notice that's the key word here, highlight, underline that, it can mean a slower reaction. Doesn't mean that it always is. Just because you have more steps doesn't necessarily mean that it's always going to be slower. But it can be. It's kind of like the first way to think about it, all right? But it could have 10 really short steps, whereas another reaction could have 2 steps, but they're very, very long. Okay? One example that I can think of is when I was in grad school, I knew organic chemists down the hall from me who would be trying to produce some new product, and one step would take 20 hours that they would just have to let the reaction set and check on it before they could then go on to the next step in their whole process. Whereas a reaction that somebody in my lab was doing would take 10 minutes, even though it took 4 or 5 different steps to get from point A to point B. All right. So just because it has more steps doesn't automatically mean that it's going to be a slower reaction. The biggest thing, this is the key that kind of determines how fast the reaction is going. That's called the rate determining step. All right. So that is the slowest step of the reaction. Okay. This is the most important factor. That's not a J. This is a semi. It's supposed to be a semicolon. All right. Most important factor influencing the reaction rate. Okay. So you're only as strong as your weakest link. That's kind of the idea here. You're only as fast as your slowest step. So if we look at this reaction here, this reaction pathway, and we're going to kind of be looking at these graphs and stuff, guys, a lot throughout this unit. Okay, A plus B plus C yields ABC. Well, that doesn't just happen in one step. Okay, we've been writing it so that reactions look like, hey, they just come together. There's a lot more going on than that. So the first step, you had to react A and B came together to produce AB. That's a slow step. And one way, and we're going to get into this more later on, when we do potential energy diagrams, one way we can see that is look at all this energy that it takes, right? That's a big hill to climb for that one step. Then once AB is formed, C comes along and reacts as well, and that's a fast step. We can see that in the reaction because it's a very, very low hill. There's not a lot of energy that's involved, so it's much, much faster. But again, you're only as weak as your weakest link, or only as strong as your weakest link. You're only as fast as your slowest step. All right, so that's what makes this process as long as it is that slow first step. All right, so let's continue on. This all comes under collision theory. We've talked about it in KMT a little bit, but now we're talking about the actual particles colliding. So in order for a reaction to occur, reactant particles must collide, kind of makes sense, right, collision theory, and have the following when they do so. So in order for them to collide, it's not just if they hit each other that the reaction will actually occur, okay? They have to have the proper amount of energy. So if they don't have enough energy to form bonds or to break bonds, nothing's going to happen. So they have to have the right amount of energy, and they also have to have proper alignment / direction / orientation. So twofold here, two pieces. They have to have enough energy to break the bonds, and if they're not oriented correctly or they're not facing each other just right, they will not come together. Okay? So this is what takes reactions so long sometimes, is that they have to be moving fast enough, have enough energy to break, but then they also have to be facing the right way, kind of like puzzle pieces. If you try to put two pieces together, okay, if I'm trying to put my fingers together like this, all right, they're not going to go together. It's trying to fit a square object in a round hole. But when they come together and they're facing the right way, we can see, hey, they come and they're locked together, bam, they've now made something new. Okay, so that's the two pieces with it. They have to have the proper amount of energy, the proper alignment. Okay. Now, in terms of reaction, a reaction that goes to what we call completion, okay, proceeds until all of one of the reactants is used up. Okay, so completion means you've completely run out of something. Now, review question here. If one of the reactants is being used up, what do we call that reactant? This is a review from way back in the mole unit, unit 3. What's that called? That reactant that runs out first. That would be your limiting reactant. Okay, the limiting reactant runs out first. Now, a lot of times we saw this in acid-base in our last unit. Reaction that can occur in both directions is a reversible reaction. And we're going to be talking about equilibrium at the second half of this unit, so we'll be dealing with reversible reactions. Eventually, though, the forward direction and the reverse reaction will reach what's called equilibrium. More on that to come. The reaction mechanism is the step-by-step sequence, all right, of the reactions in which they occur. So, this is what we've seen up until this point, this final reaction. I2 plus H2 yields 2HI. We've balanced those. We've identified it. Review question here, what type of reaction is this? If I was going to classify it, this would be a synthesis reaction. Okay, but it doesn't just happen in one step. First thing that has to happen is iodine is going to split up into two iodine atoms. Then one iodine is going to react with a hydrogen molecule to produce H2I. Then another one's going to come along to react with that to then produce 2HI. So it's not just as simple as just one step like we've seen until this point. What we're seeing down here is the net reaction. Okay, just what's left over. But there's all these other reactions that took place. Okay. Now, if you take a look at this whole reaction mechanism, all right, here's my I2 that I'm left with. Here's my H2 that I saw there. But notice all these other pieces, right? You've got I and I. You've got H2I and H2I. We notice 2 I's and H2I are on both sides, okay? They appear on both sides of the reaction. This is what's called, sorry about the bell, an intermediate. Okay? An intermediate is a species that appear in some step, but then not in the final reaction. Basically, guys, intermediates are produced and consumed in a reaction. Okay? They're produced for a short while, but then they are consumed again. So we produced 2 iodines, but they were used up. We had H2I, and it was used up. Okay, so that all in all, we only see I2 plus H2 yields 2HI. All right? So keep that in mind as we go along. All right? So what I want you guys to do, this is something you're not going to necessarily have to do, so don't stress too much about it. But I want you guys, given this mechanism, this step-by-step process, try to get the net equation from this, okay? So pause the video, cancel out the things that you see on both sides, and then just try to write the net and then identify the intermediates from that. So if I take a look for pieces that are the same. So do I see carbon on both sides? Absolutely. Now it's different because it's not just one reaction we're looking at. We're looking at two, okay? Two separate steps. But I have a carbon there and a carbon here. I don't see O2 anywhere over here, and I don't see 2CO. So everything else is my reaction. So I'm going to drop it down, kind of like our net ionic equations. So 2 carbon monoxides plus oxygen make 2 CO2s. All right, and it is balanced because you have plenty of them all. That's what our net equation would be. Now, intermediates, what was consumed and produced, okay? So these are the things you could cancel out. Now, in the last example, they were produced and then consumed, but here we started with carbon, all right, but then we also ended up with it. So that's still an intermediate. So carbon is our intermediate here. All right. Now, I know I may have just went too fast, but again, this is the only time, guys, that you're going to see it, so don't stress about this. There's much more important things that we're going to talk about within this unit. Now, one thing you need to know is how are intermediates different from spectator ions, okay? And the key here, spectator ions don't, remember, this is from our solutions unit from Unit 11. They don't take part in the reaction. They're just kind of there hanging out. They're watching. Excuse me. Intermediates, though, they take part in the reaction. All right? Meaning they are produced and consumed, or consumed and produced. All right? And the last thing to kind of just summarize reactions, guys, a little bit. If they have the same phases, the reactants in the same phase, that is called homogeneous. Should be review for us. You know, homogeneous means same. And then if they're different phases, it would be heterogeneous. Okay? So, is this homogeneous or heterogeneous? We're only looking at reactants. Okay? Only looking at the reactants. They're both gases, so this is going to be homogeneous. All right, so that's kind of just a summary of where we're going, kind of the theories behind it. So I will see you guys in the next video when we talk about those factors.